All right, we are going to pick up, and I think we have one more lecture on this chapter on elementary particle physics. And I do want to go back to this slide and say that this, along with the next couple of slides, is kind of the bulk of the chapter. That's the stuff you really want to focus on. And so let's go back and take a look at what we've got here. Just a quick review. Elementary particle physics says it's all particles. Now, we're used to maybe thinking of particles as little point objects, but you know, we've been through enough quantum physics now that you realize that any of these particles are being represented by wave functions. And so they're not necessarily located at one location in space. They're not necessarily following well-defined trajectories. They're kind of shapeshifters. So they're much more sophisticated objects than what we would typically say, oh, it's just a particle. So there's some complexity to how these particles behave, what their properties are. For the matter particles, we have two different particles, the lepton and the quark. The lepton can exist in 6 different possible lepton states, different flavor states. The flavors for the lepton are 3 different flavors of neutrino, along with 3 different flavors of charged lepton with a -1 charge. And those are the electron, muon, and tau. For the quarks, also 6 flavors of the quark. The leptons can change flavor into different types, so can the quarks. So depending on what reaction we're running, a quark can change from one flavor to the other. And the names here were down, up, strange, charm, beauty, and truth in the order of increasing mass. And in this case, it's dramatically increasing mass. And then these were the electromagnetic charges. Our understanding of quarks now explains the properties of the proton and the neutron. They never did really behave like the electron. The electron's properties were much simpler, and now we understand that's because it was a fundamental particle, whereas the proton and neutron are these kind of complicated combinations of 3 quarks being held together by a bunch of gluons. And the quarks are in different color states, red, green, and blue, or at least that's how we refer to it. And then we had moved on, so we looked at this also, and we said that, the leptons I get, the leptons are observed directly. We can directly observe the neutrinos, the electrons, the muons, the taus. Now, the neutrinos are hard to detect, so you have to build typically enormous detectors to be able to pick up just a few, but they are observed as individual particles. The quarks are not. So the way we understand quarks is by running things into protons and neutrons and generating new types of particles gives us information on how the quarks rearrange themselves. If I take a proton and I run a reaction where I try and pull the quarks apart, what I'll end up doing is all of the energy that I use in trying to pull the quarks apart generates new pairs of quark antipairs, which then divide themselves out into new particles. So quarks are always seen as composites, and we said that the 3 different composite quark systems that we have are the 3 quark combination, which is called a baryon, and the protons and neutrons are the simplest example of these. And the proton actually is the only one that's stable, and all of the other baryons decay into the proton, and that happens pretty quickly. Except the neutron survives, it's like 10 or 15 minutes. There's antibaryons, and so antiprotons and antineutrons are made out of antiquarks. Now, the mesons, none of these are stable. They're made out of a quark and an antiquark, and eventually the quark-antiquark react with each other and generate different types of particles from that. We'll look at some examples of meson decay, quark-antiquark decay. Now, the color states on the mesons, we said that they got to be red, green, or blue, but since it's a quark-antiquark system, that says, for example, this meson, I'm going to say this quark's in the blue state, and this antiquark is in the anti-blue state. So we say that the strong force works only when the combination of quarks is colorless. So blue and anti-blue kind of cancel each other out. And placing one quark in each state, red, green, and blue, also creates a net colorless state. That's how it's referred. So those are the particles that we have. Now, I don't think we got to this, so let's talk, well, we talked about this some. So in the Standard Model, the forces are also made out of particles. Anything that's happening electromagnetically is done with photons. So, I got a couple of magnets I'm playing around with, and gosh, this is amazing. These magnets are exerting forces on each other. It's done with virtual photons. So virtual photons, we're grabbing onto those virtual photons from both sides, and the forces are being exerted through those virtual photons. The weak force has three different force particles, the W plus, the W minus, and the Z, which suggests maybe we're getting close to the end of this. These are really heavy particles. So the photon is massless, but the weak particles are some of the heaviest particles we've ever observed. They're like 100 times as much mass as a proton or a neutron. So there's a charged version, plus, charged version negative, and then the Z is neutral. Three different ways that the weak force can interact. The strong force is made out of gluons, and there's actually 8 color states that go along with that. The quarks individually are in red, green, or blue states, but the gluons are a combination of color, anti-color. And if we do a little linear algebra and look at the matrix representation of all the different color, anti-color states, there's 8 of those color states that have net color to them. So there's one of those, there's 9 possible states, but one of the linear combinations has no color, and so it's not able to act as a force carrier. So we have 8 different color combinations of gluons. And then gravity's kind of down here by itself. Ooh, I left out the Higgs. We should say something about the Higgs. When the Standard Model was developed, and they looked at all of these forces, and they started drawing out Feynman diagrams to represent all of the possible processes, what they found was that there were a number of infinities, divergences. So from your calculus classes, I think in probably in Math 3B, you guys studied a series, and you found out that certain series converge, other series do not, they diverge, and that converging series can be shown to have a finite value, but diverging series are impossible to work with. There's not a number associated with a diverging series. Well, when researchers started looking at all the different ways that these particles could react within the Standard Model that they were developing, the ones that were most mathematically astute took a look at this and said, there's a problem. When we try and do predictions about how probable a certain reaction is, we end up with some of the reactions being predicted to act at an infinite rate. The calculations are done in terms of a series where each of the terms in the series is represented by Feynman diagrams, basically. And what they found was that those series would diverge. And so they couldn't come up with a meaningful number to represent those probabilities. Peter Higgs, theoretical physicist, came up with one additional new particle. And it's now known as the Higgs boson. And Higgs came up with one particle with one particular set of properties that made all of the series converge. He found the one additional interaction that through interference effects would cancel out all the infinities. So this is kind of a crazy game, but if you've got one diagram, one Feynman diagram that predicts an infinity, and you've got another Feynman diagram that predicts an exact infinity but with the opposite sign, those series cancel out, and now you're left with something that converges, and that's what the Higgs boson does. So it can be thought of as kind of a mathematical game. What kind of a particle would we need that would eliminate all of the divergences in our theory and make everything converge that we calculate? Turns out to be, it was the Higgs boson. Now the Higgs boson, probably 40 years between the time the Higgs boson was predicted to exist until it was actually discovered. But about 10 years ago it was. And it looks pretty, particle physicists are pretty confident that we really have identified the Higgs boson. So it's kind of an additional force. And it's kind of that, has that perfect set of properties. It fits that it's that last piece of the puzzle that fit exactly with all of the others. All right, so those are the force particles. Let's see how we're doing here. This slide is just reminding us that there is a weak force. It doesn't have to be nuclear. The weak force shows up outside of the nucleus. And these are W plus, W minus, and neutral Z. Now we saw the W plus and W minus back in beta decay. So we've looked at diagrams including the W's. It's also postulated that if there is to be a quantum description of gravity, there must be a force carrier, and that has been called the graviton. And if you watch episodes of Star Trek The Next Generation, they talk about gravitons all the time. But so far we don't have any confirmation of the existence of a graviton. We're not entirely sure what its properties would be. We have kind of an idea. We have some clues as to what properties it should have. All right, we are ready to look at a series of Feynman diagrams. So this is reality. So in elementary particle physics, we think of these Feynman diagrams as being the most fundamental representation of everything that happens in nature. So any sort of reaction that can take place in nature is representable in terms of a Feynman diagram. So that's kind of nice that it comes down to a series of graphs that have to follow a particular set of rules. And the graphs have a lot of information in them, so let's take a look at one. Now, the first Feynman diagram that we're going to look at here is the neutron decay. Now, this was the underlying reaction in beta minus decay, but now we're just thinking of it as just an individual neutron, and that individual neutron undergoes decay. And it decays into a proton, electron, and an antineutrino. Now, the Feynman diagram would start off with, in this case, the neutron, and identify the quark makeup. So we're not really thinking it's a neutron. What it is, it's an up, a down, and a down quark. And as time goes on, from left to right here, the neutron, the quark lines, the individual quark lines, are conserved. So quarks and leptons, the matter particles, they're all spin 1/2, they're also conserved particles. We always conserve, in all the reactions that have ever been observed, the number of leptons is conserved and the number of quarks is conserved. So I've got these three lines, and they continue all the way out the other side. Now, along the way, there was a reaction that took place along one of the lines. And this quark, which was in the down flavor state, reacted and was flipped over into the up state. And so it's coming out as an up quark. And that means the neutron that went in, because of that reaction of just one of its quarks, is now a proton. And those solid continuous lines from quark to quark is showing that in this diagram, 3 quarks went in and 3 quarks are coming out. We can account for all of the quarks. 3 went in, 3 went out. That's conservation of quark number. So the quark numbers are always conserved in these reactions. Now, these little squiggly lines that we have in here, those are the gluons. So before the reaction happened right there in the middle, there were already gluons that were holding all the quarks together. Remember, the quarks aren't going to be seen as individual particles. They're going to be seen as this bundle, and it's going to be observed as a neutron. And so all these little squiggly lines are showing that gluons are being exchanged back and forth constantly between all of these quarks, and that's what holding the quarks together to form the neutron. And it's the strong force. It's really strong. It's really holding those quarks together and forming this, well, reasonably quite very stable neutron. Same thing with the proton coming out. We're seeing the same effect. Lots and lots of these gluons making that stable as the proton comes out. Now, the reaction that took place here was a flavor change. And anytime we change flavor, it turns out we also change electric charge. So both of those have to change at the same time. The only force in nature that can change flavor is the W. So the W couples to this quark right here. Now we show the virtual W separating from the neutron to proton line. Now the W is going to couple to some other reaction. So when we have forces in nature, there's 2 reaction vertices, and one of those vertices is here, and then at the other end of that vertex is the formation of the electron antineutrino pair. Now these are also represented by a solid line, and that's to remind us that in some sense this electron and neutrino, antineutrino, are in some sense the same particle. When we create a particle-antiparticle pair, that particle-antiparticle pair is closely connected. In fact, the mathematics treats this as if the antiparticle is going backwards in time, and then when it comes forward in time, it comes out of the reaction as an electron. And that's why we've drawn a forward arrow on the electron, but not on the neutrino. All right, so let's calculate Q for this. I wrote down all the masses. There's the mass for the neutron, the proton, the electron. We can see that the neutron and proton mass is almost the same. Electron, thousands of times less. Now, each of the neutrinos, we have evidence that they have mass. They're not zero mass, but they're no more than 1 or 2 electron volts at the most. So I've just written down here, the neutrinos, maybe they're about 1 eV, maybe, and put it in parentheses, but for our purposes, it's not going to show up in our calculations. Those masses are so small, they're not going to show up. The Q for this is 0.782 MeV. So that's kind of our first example. Again, the solid lines are conserved particles. The dashed line are the force particles, which are transient. So the force particles hold a couple of the conserved particles together. All right, here's another Feynman diagram that we could take a look at. This one is muon decay, and the reaction looks like this. If we have a muon, now if you remember, oh, here it is. The muon is the heavier version of the electron. So I've got this muon, it's like 200 times as much mass as an electron, and the muon is not stable. So when the muon decays, what we see coming out of that reaction is an electron, a muon neutrino, and an anti-electron neutrino. And why is it this particular combination that always comes out? This is what always comes out of a muon decay. And that's because if I look at a muon and it's going to decay, it can only decay by changing flavor. So what's going to happen is, again, we're going to have a W, a weak force, that allows for the decay of the mu minus. Now if I look in my particle diagram, the muon is coupled in this second generation with a muon neutrino. So what that tells me is, well, the muon is going to react and turn into its neutrino. So if I'm thinking in terms of conserved particles, the muon has changed flavor. What used to be a muon flavor of lepton is now a muon neutrino flavor of lepton. Now again, the W particle here, it's a virtual particle. It is not going to be directly observed. It's going to couple to some other reaction. And so, if we're starting off with this much mass in this muon, we have to ask, well, how much mass is that? And what else could it possibly decay into? And it can only decay into something that's lower mass. Well, it turns out that all of the quarks are too heavy. The muon doesn't have anything that it could turn into made out of quarks that would be light enough. So the muon's stuck. If it's going to decay, the muon itself turns into its neutrino, and the available mass is only enough to generate an electron and an electron neutrino. So those are the only possible decay that this muon can undergo. So that's the Feynman diagram. Now again, I'm doing a Q calculation here, and this time, since we have two neutrinos, I'm going to write both of these neutrinos. Both of these neutrinos I'm going to write as roughly 1 eV. They're really low mass. So I've got a muon at 105.658 MeV and an electron at 0.511. Well, that's a lot less. There's going to be an enormous Q number on this. And sure enough, when we calculate Q, it's over 105 MeV. It's like 99.5% of the muon's mass is going into kinetic energy. So the electron is, by comparison, the electron's almost massless. We could almost consider the electron to be behaving like a massless particle in this example. So is there a way that we could look at some of the properties of these? And now in the decay that we have here, the muon decay, what I've got is I've got particle A, which is the muon, turning into three other particles. So particle B, particle C, particle D. If we have two particles that come out of a decay, we can use our formulas from special relativity, and we can determine how the Q, how the available energy gets divided up into kinetic energies. That's going to work if there's only two particles. But it turns out if you have three particles in a decay, there's a wide range of values that will still conserve energy and momentum. So there's not just one way the decay particles can come out of this reaction. There's a wide range of possible kinetic energies. The kinetic energy can get divided up very differently. So for example, let's say that the muon starts at rest, it decays into these three particles, but the electron that's produced is still at rest. Well, if the muon starts out at rest and it turns into an electron and the electron's still at rest, what are the remaining neutrinos going to do? And if none of the kinetic energy goes into the electron, then the available kinetic energy will get divided up by the two neutrinos. So, so that's what we end up with. So what happens here then is the Q value that we're working with is the 105.15. Now, if I think of this as, the way we think of it is this: instead of thinking of it as just a muon, we think of the starting particle as being a muon, and we subtract off the electron's mass. So it's not like the full mass of the muon was there. It was reduced by however much the electron's mass was. And then each of the neutrinos, we can put in the masses for those, and then we can move on and plug those values into our kinetic energy formulas. Now, this problem has enough symmetry to it that we can already predict how the energy gets divided up. If we're assuming the electron neutrino and the muon neutrino both have the same mass, then they'll divide the available energy equally. So in this case, if there's 105.15 MeV, each one of the neutrinos will get half of that. So that worked out to be 52.57. So there it is, muon decay, determining what the Q values are, and then just determining for a particular set of conditions how the kinetic energies will divide out on that. And the mass of the neutrino is just off the screen, I apologize, but that was given as 1 eV. So coming back to the reaction, let's again talk about some conservation effects here. I had one lepton that went in, and if I follow that solid line, I can see that one lepton came out. If I follow this line, what I see coming out of this reaction is one lepton, but one anti-lepton, and one lepton plus one anti-lepton adds up to be no net leptons. So the way that we implement the conservation laws, again, this solid line that connects the neutrino with the electron says that there was no gap in the lines representing that reaction. Ooh, we have another example coming up here. So we looked at neutron decay, we looked at muon decay, and now let's look at pion decay. Now a pion, we said, was an example of a meson. And the mesons were made out of a quark, anti-quark system that are attracted together. Now, in this particular example, the pion has a quark makeup. One of the quark is in the up state, and the anti-quark is in the anti-down state. And if I add plus 2/3 and minus 1/3, that's going to add up to be plus 1. So it's got an overall charge of plus 1. Now, this meson, the quark anti-quark, is being held together with gluons for a short period of time, and then it decays. So since it's a quark anti-quark, all the mesons have what you would consider to be relatively short lifetimes. Now they live long enough, we can actually see these pions go through our detectors. So they do have long enough lifetimes that they can pass through an entire detector, and we can follow their path as they are traveling through. In this case, the quark and the anti-quark react. Now again, the flavors are different. So the up flavor doesn't match the down flavor. It says that at that reaction vertex, the one right there, a flavor change took place. And the only force in nature, I know I keep coming back to these weak forces, the W is the only force in nature, the weak force, that can change flavor. So it must be at that reaction vertex, there's a W. Now, since this reaction is going to be mediated by the weak force, by a W particle, it says that at the other end, the W is going to have to end up as a particle-antiparticle pair, and it's got to be low enough in mass that the pion's mass will allow that to happen. Now, it turns out there's a couple possibilities here. One of the possibilities for the decay would be to create an E plus, an electron, an anti-electron, a positron, and its neutrino. The other possibility would be a muon and the muon neutrino. So I've got those two possibilities for the particles that are coming out from this decay. So we've gone ahead with the decay that goes into the muon. And so I've written down all the masses. The pion, if I look that up, it's got a mass of 139.570 MeV. And let me say this too, in the book there's a number of tables, and the tables are very confusing. And you don't have to, for the most part, I'll go through some of the tables, but for the most part, you don't have to work from the tables in the book. Again, they've been written in a way, they're not organized in a quick way to understand what's going on. They're kind of organized in a historical fashion that dates back 50 years. So for our purposes, we can keep coming back to this diagram as far as identifying what are the fundamental particles. If you have a particle in an example, in a homework problem or something, and it's not here, then it must be a meson or it must be a baryon. And in those cases, I would always just tell you what the quark content is. So again, the tables aren't especially useful as we would like them to be. All right, so in this reaction, I can calculate the Q. It turns out that in this case, the muon is not that much lighter than the pion, but still we've got 33.91 MeV of available energy that can go into kinetic energy of the particles. And so since this is a two-particle decay, I've got one particle to start with, and then suddenly it's split into two. These guys are going to head out with equal momentum in opposite directions, and that says that we can use our two-particle decay formula from special relativity. So that's good news. We get to use our familiar formula. That's going to enable us to go in and determine how much energy, how much of the available energy becomes kinetic energy for the neutrino, and how much of the available energy becomes kinetic energy for the muon. So these two particles are going to come out, they're going to carry, the available kinetic energy is going to get divided up between them. And so if I just take those masses and plug those into the formulas that we've been using, it tells me that the muon is going to end up with about 12% of the overall available energy, and the neutrino is going to get 88. Now we've seen this before. The particles that are lighter are going to get more kinetic energy. Since momentum is conserved, the lighter particle ends up with more of the kinetic energy. All right, so that worked out to be 4.12 MeV for the muon and 29.79 MeV for the neutrino, and those two combined add up to the total energy released in the reaction. Once I have the kinetic energies, we could also go in and say, well, how fast are they going in this particular particle decay? How fast are the particles coming out? I can get a gamma calculation, a gamma factor for each of these by taking 1 plus the kinetic energy over mc squared. For the muon, the gamma factor works out to be 1.039, and then following our formula for velocity calculations based on gamma, that says that the muon's coming out at about 27% of the speed of light. So that's the speed of the muon coming out, and that's pretty fast, 27% of the speed of light. And because of this gamma factor, the muon's going to live a little longer, right? The muon's moving in our reference frame. That means there's going to be a time dilation effect. This muon's going to survive a little longer than it would have at rest. Now, in the neutrino case, this is a little artificial because we really don't know exactly what the mass is. So what I did was I imagined that the neutrino, the muon neutrino, has a mass of 1 eV. So I thought I'll just throw that number in. If the mass of the neutrino is 1 eV, then the gamma factor on the muon is 29,790,000. That's a pretty big gamma factor. And when I calculated how fast it was traveling, and here I actually used some approximation techniques. If I just put the number straight in my calculator, it just came out as being 1. So I used some approximation techniques to determine, here's the speed of the neutrino, assuming it has a mass of 1 eV, 0.9999999999999, I think it's 15 nines, 56 times the speed of light. So you go, wow, it's getting pretty close to the speed of light, but it's not light speed yet, right, for that neutrino. And you're thinking, yeah, I could have just approximated that as being the speed of light. But sometimes, you know, it's useful to remind yourself, hey, it's not really traveling quite at light speed, but it's really close. Okay. All right, questions on that diagram? So, as far as when you start looking at homework problems, there are going to be homework problems that look like this. These are the ones to kind of latch on to and make sure that you understand well. Make sure that you understand these examples. The muon decay is a good example. The neutron decay is a good example, as well as an understanding of the Standard Model and what particles there are that make up the Standard Model. Now I think we've got a couple more examples here, so let me... So this is kind of interesting. Let's say that we've got a reaction where an electron and an anti-electron, they're headed towards each other, but it turns out they don't react. Or at least they don't react and turn into different particles. Instead, what happens is the electron and positron move towards each other. They kind of deflect, right? There's an attractive force taking place. So the path that they're taking changes, but they don't turn into any other particles. Now, how would we write that reaction? We go from A to B, 2 particles coming in. It looks kind of like the same particles are coming out. I'm going to call those C and D. Now, there's a couple of different Feynman diagrams we could write for this. In fact, for all these reactions, we're only looking at the simplest Feynman diagrams. There's always a series of ever-increasing complexity Feynman diagrams that have to be included if you're going to be doing precision calculations. So just to be aware, if you're a theorist and you're trying to really make detailed predictions, it's not enough to look at one Feynman diagram. Typically, you have to look at many, many, many Feynman variations on that. So here's the first diagram that we have here. And what this one is showing is I've got an electron coming in, and then here's the electron coming out. And I'm going to identify that as particle A coming in, particle C coming out. Now, I've got the positron also coming into the reaction, and the positron leaving the reaction. Now, since it's an antiparticle, I drew it with the arrow in the opposite direction. I don't want that to become a point of confusion. But time is going from left to right, and it's just because our convention is for an antiparticle to draw the arrows backwards. So that's a Feynman diagram right there. Now, these particles did deflect, and that says there was some kind of a reaction that took place, and the most likely reaction would be using virtual photons. So I drew that in. I drew in the symbol for a photon between those two reaction vertices. Now, that's one of the Feynman diagrams, but wait a minute. This could have happened too. There's a second Feynman diagram that is just about as simple as the first one. The second Feynman diagram suggests that the electron that went in actually reacted, and it didn't come out as an electron, but it came back out as the antiparticle. So that's saying that the E plus, E minus that I sent in actually are in some sense the same particle. There's a continuous line that connects the E minus and the E plus on the way in. So in this case, the virtual photon, it's not causing a reaction from side to side, it's causing a reaction from before and after. So the E plus, E minus react and form one virtual photon, and then that one virtual photon turns back into a new pair of E plus and E minuses. Now, the ABCD designation is telling us how these particles were actually observed. So we ran an experiment. I had a beam of electrons coming in from one direction. I had a beam of anti-electrons coming in from the other direction. And then what we saw were the electron and anti-electron came out at some angles. And so we're just asking, were the electron and anti-electron that came out, were they the same particles as the ones that went in? Or is it this diagram? And of course the answer to this is it's quantum physics, so both diagrams happened. And if you think back to, I guess the best example here was like the two-slit interference patterns that we saw back when we were looking at light, at photons. And we said to understand the interference pattern, we had to imagine that the photon had somehow taken both paths or knew about both paths, and that the interference effects came from finding an amplitude for one path and an amplitude for the other path, and then combining those together. Now, at the level of calculating the amplitudes, there could be phase differences. So what we found with photons is that path number 1 and path number 2 could be out of phase with each other, and when we calculated the probability of something happening, we had to take that interference effect into account. So it's possible, if the amplitudes were exactly out of phase, that the probability would be 0. So now we're going to take that very same argument and we're going to apply that to the two different Feynman diagrams named after Richard Feynman, well-known American physicist. And what we're going to do is do a calculation on this to find out what its amplitude is. So each one of the Feynman diagrams tells us what an amplitude is for one particular configuration. But then we have to ask, well, what were the other possible configurations? And this looks like another, maybe equally important way that the reaction could have happened. So I carry out that calculation, that gives me amplitude 2. Now, the mathematical techniques for calculating these amplitudes, we're not going to do these, but in some sense, you've already seen kind of how this works. Once we get wave functions to represent each of the particles involved, we can take all of the wave functions, line them all up together, integrate over all the possible locations in space, integrate over all the possible instances in time when this reaction could have happened, and that gives us an amplitude. So that's what we would do. We would assign a wave function to each of these four, and then we would assign a wave function to the photon. Now the difference between the two diagrams is that when we assign the wave functions, there's a mathematical technique where we pair up the wave functions that are connected to each other. So for example, in the first diagram, the wave function for particle A and particle C, well, that's a continuous line, so those two wave functions would be coupled together. There's some additional calculations that we do on those. And B and D go together. So the wave functions for B and D would be calculated as a packet. And then once those are calculated, they're combined with the photon, and then we carry out the whole integration. Now again, this is not something required in the course. It's just for, I mean, if this is going to be reality, you might as well have a kind of a conceptual idea of how these calculations are done. Now, we do the same thing with diagram 2, but notice in diagram 2, A is not connected to particle C. The wave function from A goes together with the wave function from B. So here, kind of schematically, I've put those two wave functions next to each other to show that they need to be calculated combined as a pairing, and that C and D are the other pairing, and then the photon calculation couples those two, what are called currents. We carry out the same integration there. So this diagram gives us an amplitude, this diagram gives us an amplitude, and in general, those amplitudes can have different phases. So they could be in phase with each other, or they could be out of phase with each other by varying amounts. So to calculate the probability of that initial reaction that we wrote down, we have to calculate amplitude 1, calculate amplitude, add them together. In that addition process, interference effects could come into play, and then we modulus square that, and that gives us our probability. So it's a crazy set of rules, but this particular crazy set of rules is kind of foundational for elementary particle physics, and it works really well. So if we've missed something and we're doing something wrong, at this point we're not clear what that would be. Every experiment that's been measured over the past 50 years has agreed with the predictions made using the standard model. 50 years ago, the standard model made a prediction of the existence of, I'm going to say, somewhere between 8, 9, maybe 10 particles. And over the years, each one of those has been identified. So it's a remarkable story in elementary particle physics. And I myself was in that field, and I feel fortunate because I kind of came into that field at the time when the standard model was being developed. So I was able to, be in my educational whatever at the time when many of these new ideas. So, I came in at a good time as far as seeing how the theory would develop. These are just some more pictures of detectors. So, trying to see if there's anything here that would tell us. Not sure which experimental lab these are coming from, but that's an example. We have a beam pipe, particles come in, reactions happen, and sprays of particles come out in different directions. If you can get simpler reactions with only a few particles coming out, it's easier. But sometimes when you go to higher energies, you just get more and more. Now here's some tables from the book. So I just wanted to point to what I feel like is useful and maybe what you don't have to pay as close attention to. This isn't so bad. I mean, here's the strong force, electromagnetic, weak, and gravity. And they're just saying, kind of with the reactions that we run, what's the relative strength? And if we say the strong force, which is the strongest, if we give that a relative strength of 1, then we say that the electromagnetic force is only 1/100th as strong. The strong force is 100 times stronger than the electromagnetic force, and it needs to be, because it has to be able to pack all those protons into a nucleus and hold them together. Now the weak force is like 1,000,000 times weaker. So that's much, much weaker than the strong force. And then finally, gravity, which isn't part of the standard model, but just as a force, gravity, well, it's hard to compare here, but this is saying approximate relative strength for 2 protons and a neutron. in a nucleus. But gravity is considered to be much, much, much weaker. Now, so that's, and then the particles that make this up, the gluons make up the strong force, photons make up electromagnetics, W's and Z's, and then the speculated existence of a graviton for gravity. Here we're just reminding ourselves that for most of the particles we've looked at, there is an antiparticle that goes along with that. Now, some particles are their own antiparticle. A photon, for example, there's no antiphoton. It turns out the photon and the antiphoton are the same particle. If you reverse the properties on a photon, it still looks like a photon. Now, neutrinos aren't like that. Even though the neutrinos are neutral, when you reverse the properties on a neutrino, you can see you get a particle with distinct properties. And it has to do with how the neutrinos couple to the weak force. So there definitely are neutrinos and antineutrinos, whereas photons are photons or photons. Here's one of those tables from the book that it's okay to look at it. I mean, here, let's just take a quick look. Here are what we've looked at as the truly fundamental particles. The gauge bosons is a name we use to talk about the force carriers. So photons, gluons, W's, and Z's. And then it's talking about the antiparticles here too. And then we have a collection of leptons, and those are all listed. Now what's missing here is they didn't give us a quark table. Instead of giving us a quark table, what they did was they gave us a meson and baryon table, and that's too complicated. Now, I'm sure I assigned one, maybe two homework problems that kind of expect you to go through and look at all this. I'm going to say don't worry about those. Okay, for our purposes, I'm not going to send you off into this table to try and look at all the properties. Now, up here, the ones above, these are the fundamental particles. So those are kind of interesting to look at and look at the comparison on their properties. Okay. Here's a reminder of how quarks can combine. So here is the quark makeup of a proton, the quark makeup of a neutron. The three quarks inside are, one's in each of the possible color states. And then the flavors are determining what overall charge they'll have. Here is the pi plus, here is the pi minus. We looked at those. Here's a kaon, which has a strange quark. Instead of a down quark it's connected with, it's a strange quark. So it's a little heavier, but you can make these particles from any of the flavors of the quarks. So whatever flavor you come up with. Now here, later in the chapter, they finally come up with an individual table giving us properties of the quarks. So we've got the 6 quark flavors in there. We got the ups and downs, strange and charm, bottom and top. They didn't say beauty and truth. And look at the range of masses. Now these are hard to determine. There's going to be some speculation on what the masses of these are, but they range all the way from 2 MeV to 173,000 MeV. So the top quark is the heaviest particle that we've ever observed. And it has a mass, it's about 200 times the mass of a proton or a neutron. So enormous masses. The charges are given. Now there's something called baryon number, which is counting the number of baryons. We're using kind of quark number in place of that. And so you don't have to worry about the baryon number, the strangeness, the charm, the bottomness, the topness. That's all pretty simple. But, spend some time looking at those range of masses. Again, it's kind of remarkable that top quark, it's like 40 or 50 times more mass than any of the other quarks. And again, the question becomes, why is that? Why do we have that pattern? Now, here is another set of mesons and baryons. And again, this is a table I don't think you need to spend a lot of time on. it's not worth spending a lot of time looking at all of the different combinations. Okay, finally a couple things to say. There are these grand unified theories. The idea that eventually all the forces, the strong, the weak, the electromagnetic, and even possibly gravity, could really be all parts of the same force once we go up to high energy. Once you go up to high energy, the masses of the individual particles become negligible, and it could look more and more as if all of these forces are subsets of some overall force. Now, these sorts of ideas have been worked on for 50 years, and so far we don't have any theory that works. We don't have any theory that works that explains all of the forces in nature. So, you know, maybe the standard model is the standard model. Maybe that's going to be it. Here's a summary here. Very quickly, we looked at accelerators and some of their properties. We looked at the different forces, the different matter particles, 6 quarks and 6 leptons. So you can take kind of a look at that list. But we're going to end it right there for chapter 43 and elementary particle physics.